Hello everyone, welcome to my poster presentation on the topic of satellite-to-ground quantum key distribution with adaptive optics. I will first start by explaining the motivation of this study. QKD terrestrial implementations are limited to distances of several hundred kilometers due to the exponential attenuation of optical fiber and the lack of mature quantum repeater technology. In order to implement larger-scale quantum-secure networks, satellite-to-ground QKD links become a promising solution. However, atmospheric transmission comes with its own set of drawbacks, namely the perturbation of the optical wave by the atmospheric turbulence. For this feasibility study, we considered a downlink communication with a low Earth orbit satellite in both day and nighttime at telecom wavelength. And we considered that the light is going to be coupled into a single mode fiber at Bob's receiver. In order to partially mitigate the aberrated waveform, we consider the inclusion of an adaptive optics system, which is basically a feedback loop consisting of a waveform sensor capable of detecting the aberrations, a real-time computer that takes these measurements, and according to them sends commands to a deformable mirror that will make the necessary adjustments. Our methodology for this study consisted on first modeling the atmospheric channel by constructing turbulence profiles, as the ones you see in the picture, uh, from different experimental databases. With this, a certain adaptive optics configuration and for a certain satellite orbit, our simplified simulation tool allows for the computation of the effects of turbulence and its correction on the coupling into a single mode fiber. In parallel, we also simulate the effects of beam wandering due to the pointing jitter of the satellite. We will then combine both of these statistics in order to obtain the transmission efficiency through a whole satellite path. This will allow us to finally estimate the key rate. On the left is an example of the type of finite probability distributions that we obtain for satellite paths, in this case for different turbulence strength conditions. So, for example, D3 is a stronger turbulence profile, which can be noted by the fact that the transmission efficiency values are skewed to the lower values. The key rate is then estimated according to these distributions, and for CVQKD, we consider a Gaussian modulation protocol with coherent detection, and for DVQKD, we consider a decoy state efficient BB84. Here are some of the results we obtained. On the left, we can observe by the formulas that the key rate in both cases is going to depend on the transmission efficiency, either directly in the case of CVQKD or indirectly through the QBR in the case of DVQKD. The figures on the right show the resulting key rate for different satellite altitudes with and without adaptive optics correction, for different noise levels, and even taking into account the finite size effects. All of this was done for a moderate turbulent daytime profile. We can observe that using a somewhat complex but still realistic adaptive optics system not only increases the overall maximum key rates that can be obtained, as well as extend the distances in which we can feasibly obtain a key, but it also permits the extraction of a key in the case of a more realistic finite size simulations, which are noted here by the dashed lines, that do not exist in the case when we don't consider adaptive optics correction. This effect is even more noticeable in the case of continuous variable QKD, in which we can increase the maximum key rates by almost 3 orders of magnitude. So in conclusion, taking into account finite size effects, we need an adaptive optics correction of at least 5 orders, 10 to 15 orders in the case that we want to treat a stronger turbulence profile. Thank you very much for your attention.